Welcome back. In the last video, we set up some device agnostic code and we got ready to start putting everything we've learned together. So now let's continue with that. We're going to recreate some data. Now we could just copy this code, but we're going to write it out together so we can have some practice creating a dummy data set. And we want to get to about this stage in this video. So we want to have some data that we can plot so that we can build a model to, once again, learn on the blue dots to predict the green dots. So we'll come down here, data. I'm going to get out of this as well so that we have a bit more room. Let's now create some data using the linear regression formula of y equals weight times features plus bias. And you may have heard this as y equals mx plus c or mx plus b or something like that, or you can substitute these for different names. Images, when I learned this in high school, it was y equals mx plus c. Yours might be slightly different. Yeah, bx plus a. That's what they use here. Whole bunch of different ways to name things, but they're all describing the same thing. So let's see this in code rather than formulaic examples. So we're going to create our weight, which is 0.7, and a bias, which is 0.3. These are the values we previously used. For a challenge, you could change these to 0.1 maybe, and 0.2. These could be whatever values you'd like to set them as. So weight and bias, the principle is going to be the same thing. We're going to try and build a model to estimate these values. So we're going to start at 0, and we're going to end at 1. So we can just create a straight line, and we're going to fill in those between 0 and 1 with a step of 0.02. And now we'll create the x and y features, x and y, which is features and labels actually. So x is our features and y are our labels. X equals torch.arange, and x is a capital. Why is that? Because typically x is a feature matrix. Even though ours is just a vector now, we're going to unsqueeze this so we don't run into dimensionality issues later on. You can check this for yourself. Without unsqueeze, errors will pop up. And y equals weight times x plus bias. You see how we're going a little bit faster now? This is sort of the pace that we're going to start going for things that we've already covered. If we haven't covered something, we'll slow down. But if we have covered something, I'm going to step it through. We're going to start speeding things up a little. So if we get some values here, wonderful. We've got some x values and they correlate to some y values. We're going to try and use the training values of x to predict the training values of y and subsequently for the test values. Oh, and speaking of training and test values, how about we split the data? So let's split the data. Split data. So we'll create the train split equals int 0.8. We're going to use 80%, which is where 0.8 comes from, for the length of x. So we use 80% of our samples for the training, which is a typical training and test split, 80-20, thereabouts. You could use like 70-30, you could use 90-10. It all depends on how much data you have. There's a lot of things in machine learning that are quite flexible. Train split, we're going to index on our data here so that we can create our splits. Google Colab auto-corrected my code in a non-helpful way just then. And we're going to do the opposite split for the testing data. Now let's have a look at the lengths of these. If my calculations are correct, we should have about 40 training samples and 10 testing samples. And again, this may change in the future. When you work with larger data sets, you might have 100,000 training samples and 20,000 testing samples. The ratio will often be quite similar. And then let's plot what's going on here. So plot the data and note if you don't have the plot predictions function loaded, this will error. So we can just run plot predictions here if we wanted to, and we'll pass it in xtrain, ytrain, xtest, ytest. And this should come up with our plot. Wonderful. So we've just recreated the data that we've been previously using. We've got blue dots to predict green dots. But if this function errors out because you've started the notebook from here, right, from this cell, and you've gone down from there. Just remember, you'll just have to go up here and copy this function. We don't have to do it because we've run all the cells, but if you haven't run that cell previously, you could put it here and then run it, and we'll get the same outcome here. Wonderful. So, what's next? Well, if we go back to our workflow, we've just created some data. And have we turned it into tensors yet? I think it's just still, oh yeah, it is. It's tensors because we use PyTorch to create it. But now we're up to building or picking a model. So we've built a model previously. We did that back in build model. So you could refer to that code and try to build a model to fit the data that's going on here. So that's your challenge for the next video. So building a PyTorch linear model. And why do we call it linear? Because linear refers to a straight line. What's non-linear? Non-straight. So I'll see you in the next video. Give it a shot before we get there, but we're going to build a PyTorch linear model.